it was more, I don't know, like more traffic. The sensation that it was a bit more, crowded than other days. Because we were coming with the Uber, and the Uber actually was also, struggling there with the buses, some cars. I don't know. And it was not raining. Supposed to be better. We haven't used it. We are sharing something together. In Barcelona, I always go with the metro, but here, since we have to be here on time, and we have to make 3 connections, you arrive all wet, sweating with the hot. Do you have air conditioning inside the trains? Do you have air conditioning? No. Yeah, you do?
You want to start? I mean, you can start with some review and then...
Exactly. Yeah, my idea was just to remind them.
Yeah, that's right. So please, Carmen.
Yes, thank you very much, Marcos. Okay, so welcome back this morning. Remember that yesterday we started this second topic in which my group actually these days is doing research. And it's about these fish that we have in this tank. And I told you that these 2 parts are not really disconnected, because although maybe the models that I'm going to present to you actually are not related to decision making, which is what we were talking in the first 2 lectures, they are doing some decision making while they move in order to choose what is the next step, what is the next direction. But actually they want to go together because this is a group species. They like to live in groups. They don't like to separate. And I told you already yesterday that the moment in which you put 2 fish in the tank, they will just find each other at some point, and they will stay together for the rest of the experiment and until we decide to put them back into the resting home. Okay? So it's true that, this for a course, well, you don't have the fish, maybe, but I must tell you that some of our data are available already in GitHub. So you can go there and download some of this data, digital data that we have used in order to do our research. So I know that maybe if you are not doing animal collective behavior or animal motion or something like that, maybe it's something that you don't want to do, but it is for you, actually, it's up to you to go download the data and try to do yourselves the measurements that I'm going to show you in the following slides, okay? So remember that one thing that it is peculiar and that usually not so many people are taking into account in these models that several people already have published in the literature to describe the collective motion of this fish school is this glide, what we call the burst and coast or burst and glide. So the idea that they use the caudal fin to propel themselves, accelerate, and then they let themselves go, as you see in this little video that you have downstairs. As a result, even if they go together, you will see that the velocity, the average velocity of the group, or speed, I have the tendency to call it velocity, but it is the modulus of the velocity. I told you already yesterday. The speed is undergoing as a function of time this, some sort of quasi-periodicity, whatever you want to call it, okay? And I was proposing you, remember, an exercise, the first, well, I show you that, there is also a correlation in between the behavior of this speed and the behavior of what we call the polarization, which is something that you have to have in mind, because it's the way to measure order in these schools, in these fish schools. So the idea that when they move, they point together, towards the same direction. And this is obtained through this parameter, which is an order parameter, which sums vectorially all the velocities normalized, because here we are only interested in the direction, in the order regarding the orientation. And I show you this last graph in which you see that there is some sort of connection in between what the velocity is doing and what the polarization is doing as a function of time. And I already even told you that the best correlations that you can find in between these 2 observables are not if you compare them at exactly the same time, but if you allow, some jet lag, like mine, some lag in between the two observables, and you calculate, for instance, the velocity at time t and the polarization at time t plus tau. Tau being some extra time that you will have to give the system in order to organize itself according to the value of the velocity of the group at that particular time. Okay, so you change velocity, and it will take some time. There is a little bit of delay until the system gets used to that new velocity and organizes itself according to that new velocity.
And this plot takes what sample?
No, I have one, but I didn't put it here. But what you can imagine that I don't have here is that you can calculate the correlations of B of t and phi at time t plus tau, and they will be very similar, but a little bit higher, a little better, so closer to 1. So feel free, as I told you the first day. Sorry, Albert. So feel free, please, to interrupt me at any time. Maybe even you can help me because, I'm just having some trouble in order to speak continuously. Feel free to interrupt me. You don't understand anything, or if you want to clarify something. It makes no sense that you stay here without really getting what I am doing. So I know it's easy, but still, if there is some doubt or some point that you don't see clear, please let me know. Okay, so understanding this, well, for us, maybe, it's easy to see, intellectually that this has to be like that, that they move and that they're not synchronized because otherwise, they don't move together. So they have to do something that is like the velocity, the same for everybody. Otherwise, the group will split into pieces. And this is something that for them, is not allowed. Nature actually has programmed them in order to stay together. And if there are not mismatches, very big mismatches in the velocity, they will actually won't be able to stay together. So they have to actually update their state of motion in order to keep together with the group. What can they do? The idea is that they can control the time that they spend beating the tail in order to accelerate. So they can do that faster in order to go faster and not getting lost behind. And also they can control the time that they stay just gliding without really spending energy. So they can adjust these times that they actually invest in beating the tail and in relaxing. And by doing that, they are able of synchronize. This is a possibility. But there are other possibilities out there. So yesterday I was proposing you this exercise because I thought that maybe you were all familiar with this simple big check model. So I was proposing you this fourth exercise in my course that was to ask, for instance, ChatGPT to generate a big check code for you with periodic boundary conditions. And the code actually will have the velocity that is constant, because this is the normal definition of the big check model. Any question about it? So the idea is that you only care about the orientation that is going to, each agent is going to take at time t plus delta t, according to what the others, including himself, are doing at time t. And the only thing that we care about is the average orientation. So you have to sum all these vectors in your neighborhood, extract what is their final vector, and from that vector extract what is the average orientation. And this is what you are going to imitate next time step. And you are going to add some noise, some extra noise, with eta being a uniform variable, distributed in between 0 and 1. And since this is an angle, then we are going to multiply it by this variable here. That is something that goes in between minus pi and pi, because this is the angular dependence that we are going to consider. Within minus pi and pi, this is the usual way to model this. It's very easy, so I recommend, even if you don't work in collective animal behavior, I think that it's very recommendable to have some code like that, and then just play a little bit around with it. You can do many things. The first thing that I wanted to propose to you yesterday, and I did, was that you, first of all, this is the type of results that you will have. This is just a system that is very small. I think that 300, you see up there, 300 agents. And you see that they enter and re-enter again because there are periodic boundary conditions, so you are not losing any animal. You don't have to decide what to do at the walls. It's just very simple. Whatever gets out from one side gets in from the other. And you see the formation of these bands. That is something that is natural in this model due to the periodic boundary conditions and from the fact that, these species are going around and around. Eventually, they organize themselves if the density is high enough in the form of these bands that you've seen. But one thing that, the movie was illustrating, maybe I go back, is that at some point I passed from everybody moving at a very slow velocity to everybody moving at a slightly higher velocity. And maybe the arrow is actually marking where I do that, this transition from from low velocity to higher velocity. And then you eventually notice that there is a jump also in the ordering, which is measured in this graph here. So this is the polarization as a function of time for this particular realization of the simulations. So what do I want to tell you with that? That the big check model, the results that you will get for this order parameter that it is measuring the order, is actually very sensitive to several things. First of all, the density. If the system is very dilute, if you don't have too many fish, you don't see anybody around you. So the order is not possible and the system will remain disordered. Second, noise. There is a noise, I told you. If this noise, that you can imagine like a temperature in this system, that it is actually out of equilibrium, so you don't verify detail balance and things like that. But still, you can intuitively imagine that this noise is like a temperature that is allowing the system to do things. So this noise being very big, of course, is against the system developing such a big order. So in the end, you are going to have something that it is with a polarization that is very close to zero. On the other hand, if the noise is very low, then these interactions in your neighborhood trying to imitate your neighbors then are going to provide you the possibility of having an ordered pack of particles that it is moving together. Ordered in the sense of orientation. Don't remember that. It's not a solid, a crystal that it is moving together. Here there is no attraction and repulsion. The only forces are forces that are like in the XY model. I told you yesterday, but it seems that not everybody knew what is the XY model. So it's just the ordering of the spins that we have seen also modelized through the Kuramoto oscillator, something similar. Okay, so what I wanted to say is that also the big check results will depend on the basal velocity of the agents. Everybody's moving with the same velocity. If they move fast or if they move slow, the possibilities of encountering other particles are changing. And actually what you see in this simple exercise is that the higher the velocity, actually the higher the order that you will see in the system. Okay, this is an observation that is already published in the literature and that you can easily reproduce with small systems. It's really very easy. So now, what I was proposing to you is that you use this idea that the velocity affects the order in order to be able to describe these polarization changes that we were seeing in the real experiments. And remember that my aim today is going to be proposing models that are able not to describe the data, the experimental data. These are going to be data-driven models. And they can be very simple, such as this that I am proposing you, or they can be a little bit more sophisticated, and they are coming in a while. Okay? So this one actually is very simple, just to have fun if you want. So the idea is that I was proposing you to simulate this big check model, but now with a velocity at the level of each agent, that it is periodic, for instance, or that it is a triangular function. It doesn't really matter. You can play with whatever type of velocity input and try to see what do you get as an output. So since the velocity matters in order to determine which kind of order you have in your system, this is the results that you will get for different values of the noise by changing the velocity of the particles. This is the values of the order parameter that you will have. Here, not very sensitive to that, but as soon as you reduce the disorder, more and more sensitive to the changes in the value of the velocity. So then, the idea is that you are going to make the velocity actually move in between here and here, for instance, a place where the velocity has allowed the system to reach the maximum order for a particular level of noise, to a place for low velocities where the orientation is going to feel that, the system is a little bit more disordered. Sorry, the polarization is going to feel that the system is more disordered. So the idea is that I am going to do that. Each agent is going to be varying its velocity according to this periodic function that will allow, if I leave the system enough time, to go in between here and here. But, the frequency, the period of the signal is something that you can actually tune And maybe the system needs more time to get used to the new value of the velocity. So if you don't have enough time to reorganize yourself according to the new value of the velocity, something in between is what you are going to see. And this is what you are going to see. So imagine that you will move steadily with the same velocity equal to 3, approximately 3. You will get this polarization, very high. It's this point here. Now I'm implementing that each agent is moving according to this signal for the speed. So then the polarization that you are going to get is the red signal that you see here. So very similar to what I was showing you, at least qualitatively in the experiments. So with a model such as that, which is trivial, so I'm just plugging in agents that do the burst and coast independently and all at the same pace. So synchronized, by definition, by construction. I didn't explain you how did they do that, but here I'm just trying what happens if I do that. Then if I do that, my polarization will resemble very much that I see in the experiments. And maybe you can even continue and change the value of the frequency. This is an exercise that I was proposing to you, and I'm very welcome to help you doing that if you need any help. So by changing the period or the frequency of this oscillatory signal, there are differences in the results, and actually you can compare what you get for the different periods with the experimental signal and try to see whether that period that you have plugged in makes some sense from the experimental point of view. And there is a period for which you will have a distribution of the polarization that resembles very much that you get experimentally, which is depicted here in blue in the histogram. So the histogram is the experimental data. Okay? Not very bad. So that model should be a good model. It can be a good model if you are only interested in explaining the polarization that you see in your experiments. But probably that's not enough, right? Because I didn't explain you what makes these fish synchronize their up and down motion in such an effective way so that you can have such behavior for the polarization. So now I'm going to try to connect a little bit with the talks of Ulrike. So I saw this paper. It's a very recent paper, and I want your feedback, because I'm not an expert in synchronization. There are other experts here in the audience. But the idea is that these guys here, and they are not everybody. I mean, I think this person here has a book on collective motion. He's working in Sweden, I think. And they have published this paper in this journal of the Royal Society, in which they propose to combine neuronal dynamics, what happens really in the brain of fish, with what they actually exhibit as a signature of their motion. So the idea is that they propose, in order to explain this synchronization of their speed variations, they propose that there is some sort of burstiness potential inside them, which will be similar to this membrane potential that the neurons actually use. And then there is this slow whatever recovery function that in here for fish to explain the behavior. This is the behavior of a single fish, just one fish, trying to reproduce what's going on in order for it to actually show this burst and coast behavior. So the idea is that you have this burst potential, and I think this is similar to the Fish-Nagumo model, Fishwood-Nagumo model. I think that's what is written in the paper, and I recognize some of the terms in your equations. But there is this constant here that I didn't see in your equations yesterday, but I don't know whether you can add that. This is a constant, and this constant actually is very relevant. I'm going to explain it in a moment. And then for the other variable that it is this recovery, that it is coupled to this action potential, to this membrane potential, they propose that now is the velocity, or the speed of the fish. So what does this other equation say? The idea is that if this action potential is such that actually, here they also, this is the bad part of probably this model, but I'm not sure if it's bad. The idea is that instead of what you have in neurons, that you will have here the effect of this variable linearly, here they substitute the dependence of this B potential here by this function that it is a sigmoid. I don't know if this is another type of models that people in neurons also use very much, but maybe they should have started with the linear, and maybe it doesn't work. I don't know. They don't say that. This is what we usually do. If something doesn't work, you don't say it. But instead of making it easy, they propose already that this function is not just a linear function, but it is a sigmoid with lots of parameters. So, okay, that's not so good. But anyway, I'm not proposing the model, so criticizing is always very easy. I mean, you have to be constructive. So the idea is that when this right-hand side of this equation is greater than 0, then you accelerate. So your burstiness inside, your state of mind is bursting, and then you speed up. Whereas, I mean, due to the shape of this sigmoid function and the combination with this friction that you have here, when this is negative, the idea is that you relax, and it's giving rise to this type of, this is the internal variable, and this is the velocity. So the velocity will be doing something like that at the level of the fish. Just by coupling, as I was telling you, the neuronal dynamics, and reflecting this neuronal dynamics, this internal state of the brain with the speed. Okay? So it's a possible model, why not, to explain, well, there are many parameters. And actually, what it was very surprising to me, so maybe the experts here in the audience, is that this constant here appears to be very important, you will see in a moment, because with that you change very much both the frequency of the signal and also the amplitude. But the change that you see here, which is not, I mean, is noticeable, I mean, it's just introduced by a change in this parameter, which is of the order of 0.05. So the system seems to be very sensitive to the value of this parameter, and I don't know if it's normal, because, I mean, yeah, if it's so much about not fitting some parameters, it's a little bit, at least to me, it's a little bit, Okay, but this is just for one fish, and I forgot to mention that this is a motion of one fish in one channel, that it is almost one-dimensional. Now, what they are going to do is to continue proposing this type of mechanism in order to understand the dynamics of two fish, such as the ones that I was showing to you yesterday. My experiments are in 2D, in 100, in a square meter tank. And here they propose to study this in a one-dimensional channel. So actually, the positions of the fish cannot be the same as in 2D. But in any case, they compare also with other experiments, and the experiments are like mine, in a tank that it is 1 square meter, and in 2D. So, well, I don't know also what is the validity of this if you go to the two-dimensional case. So let me show you what happens if you have two fish. So they just repeat the same equations at the level of this burst potential, this burstiness, this internal state of your brain that allows you to accelerate for each fish. And now they have to connect the two fishes. How do they do that? So they introduce ad hoc, probably, this function here, which is, again, a sigmoid that has this particular shape. So in words, it's not that difficult what they do here. The idea is that if you are behind, this function is going to contribute and add up to this constant that was so important to change your state of velocity. If you are behind, you want to burst because you don't want to be let out behind. Whereas, I mean, if you are in front, actually, this function is going to be negative, and then you don't do anything. So this doesn't add to the constant C that it is crucial in order to get what you want. You see? So the idea is that if you lay behind, you are adding this function that depends on the relative position of the two fish. It's going to contribute either positive or negative. If it's positive, actually touches this parameter that sets in the characteristics of the motion. If it's 0, you just stay the way you are. So if you were gliding, you will continue gliding. So this is what they do, and I don't know if it's a good model. I mean, we will have chances to talk, because it's a nice way to put together the fields of synchronization and collective animal motion. So the idea, I thought, it looks interesting. And not only the idea, but also the results, maybe too much, I don't know. So the idea here is that by touching one parameter that appears in this function, this D here, which is some characteristic distance, that actually changes the behavior of this sigmoid. So they can generate lots of different patterns deterministically, no noise in this model, so everything is deterministic. And the idea is that by touching a little bit this parameter, they can pass from just both fish reaching a steady state in which they keep the same positions for the rest of the time after a little transient, to a situation by changing just very mildly this parameter D to a situation in which they remember the exchange of leaderships that we were discussing yesterday. So the second situation that I am describing here, that just implies the change of this D parameter that appears here actually predicts that you have this aperiodic or something no more chaotic exchange of leadership, who is going first, who is going second. So they change as a function of time, which is something that we observe in fish. By changing it a little bit more, always in the up direction, actually you pass from this aperiodicity or chaotic exchange of leadership to this more regular exchange. So one is the leader first, and the second is the follower, and they actually go the opposite way around, and this is happening at no particular periods or windows of time, after some windows of time. I don't know, but I found that, it was something, well, lots of parameters is true, but, and then you can have also permanent leaders, so by increasing a little bit more this parameter, there is only one that it is always going to be the first, and always, the second is going to be behind. And here, I think that they just keep, just oscillating, regularly, but again, there is no leader in here, so I don't know what does it mean. But I think that, it's like this, right? But the motion is much more regular. Anyway, whatever. So with this simple model for two fish, combining their mind state, their internal whatever neuronal state with the motion, they are able to produce all these patterns. And they can compare also, and in the paper they do it, so this is a suggested reading. This is another homework that I give you. They can compare with experimental data. So in here they are comparing with experimental data. This is the experimental data for fish that are guppies. It's another kind that many people will study in the lab. And this is the model for one particular set of the parameters. And let me tell you that, yeah, these experiments are also like mine, in 2D, in a tank that it is 1 square meter. But what they say here, if you read it, is that they are only going to get pieces of the experiments in order to compare with the model, in which the fish actually, the trajectories of the fish don't deviate more than 45 degrees. So the idea is that they get like straight line pieces of the trajectories in order to compare. They forget about the turning, that, of course, because they are in a closed space, and so on and so forth. Well, I don't know. This is what there is, and they publish this paper, and I think that the comparison here, they compare the speed with respect to the relative distance in between the fish, one being in the center of reference. And this is the model, much more regular because it's the deterministic model, although it's chaotic, but compared to what happens in fish, it seems that the noise still is necessary, right? Because it looks like, but it is not quite like the same. And the velocity of the experiments and the velocity in the model for the same parameters. So, okay, it's up to you to believe whether the model is good or maybe, still some work is needed. In my opinion, yeah, I don't like too many adjustable parameters. Maybe one should try just to use the model, as it is, not complicating it more with more parameters. And still, I see that there are lots of discrepancies, but maybe it's also because the experiment shouldn't be compared with a model in one dimension. Maybe you can generalize and do some work in 2D and try to see if it's better. Okay, so this is something that it is open. I haven't worked on that, but I thought that it was a nice paper that has to do with the conference and puts the two topics together. Okay? And there is no more generalization than the two fish. So if you have N fish, they don't say. Okay, so that's an open way, again, for research. And also, along the same line, so here, so take into account that what they wanted to do is to take into account your internal brain state, so your neural activity, in order to, connect it with the patterns of motion, at the level of single fish, and connecting the two of them through this particular phenomenological model. But now, you are going to hear today the talk by Albert, and there are also the people out there in the literature that has proposed similar things, in the sense that there is an internal variable, such as a phase oscillator inside each agent, that it is self-propelled, and that actually, but it is not thought to be in the opposite way around. So the idea is that by using motion, you can synchronize the internal state that it is describing maybe your neuronal activity. So in the other example, it was the other way around, right? So the idea is that you use the internal activity in order to coordinate and to give the features of the motion of fish. Here is the opposite way around. You use the normal motion. Here is just self-propelled particles, such as in the big check model, right? But a little bit more sophisticated. There are disks here that are moving. And Albert probably will tell us this afternoon about this. And they use the motion here in this paper in order to get the synchronization of the internal state of the mind. But the internal state of the mind here is not affecting the motion, right? So, no? Oh, yes. So the state, internal state, is also reflected in the kind of motion. Yes, okay. So, Albert knows much better. And this is another suggested reading. Okay, so this is another attempt to put the two things together, which is very nice. And I recommend that you read it. Okay, but apart from kinematics, like velocities, and trajectories that we have been describing, of course, you can get also information in the experiments about the structure and the networks, that many of you are also interested. These networks are very easy because are fish that are in contact. We usually characterize what we call the Voronoi neighbors, who is neighbor of whom, cannot be, closer to any other particle in space than to that one that actually is called a neighbor, a Voronoi neighbor. So this is what we do here. And actually, before that. And here, this is just a snapshot. But the idea is that this is something that it is going to be moving around in time. And then you can see whether there is a persistence in the contacts, whether these contacts are being reshuffled very fast in time, and it's very deformable, the system inside, all these kinds of informations are available to us as well. So what do we do with those things? For instance, this is something that it is unfinished, so I don't have the time now to tell you. But the idea is that we don't want to have the full picture of the motion in the tank, but just following and sitting on top of what we call the system of reference, that it is centered at the center of mass, at the centroid of the group. So you move with the average velocity of the group together in the same direction with the group. And then you see how the fluctuations with respect to that average motion. And this is what you will see. So you see that it is something looks like a droplet with some weird tension, line tension or surface tension. In this case, it's two-dimensional, so it's a line tension. And this can help you, and this is what we want to do, although I'm going to explain you models in which there are also parameters. But this is actually something that it is nice that the statistical physicists, by using some simplifications and maybe going to these systems of reference, we can try to make models that are a little bit more coarse-grained. So here, you see this, and maybe we can use a model in which we have this blue line, which is representing what we call the radius of gyration of the group. So the radius of gyration is just an average measure of the size of the group and the fluctuations in this co-moving reference system. So the idea is that you are going to represent the group of fish that is moving with the center of mass as if it was like a kind of a droplet that it is exhibiting this type of pulses, these fluctuations in time, right? And for that, actually, you can try to write models that both try to describe in a more coarse-grained and effective way a particle that it is moving some sort of a potential that is allowing the system to do that, and quantifying a little bit the type of noise that maybe will be necessary in order to actually do that and compare well with the experiments, things like that. So there will be effective theories of one particle in an effective external field, something like that. Something that we have discovered that is very nice is that imagine that I get these shapes, these pulsating balls that you've seen before, and then you average them over time, and then you have this sensation that you have these droplets. This is for different system sizes. This is a system that it is smaller, I don't remember, maybe a few fish, and the number of fish are increasing as we go from the left to the right. So the idea is that you have this droplet, and the droplet has an inside core, which is what it is inside the radius of gyration, that it is pretty much uniformly occupied. So the density of occupation of fish there inside what we call the radius of gyration is going to be kind of flat, not changing very much, because in the end they don't occupy the space that it is. Remember that we were characterizing. Maybe I go a little bit more slowly because if it's new for you. So there is this space in which fish actually, other fish, here we have a focal fish in the middle, and in blue around it, and taking into account, and this is experimental data. So around it, you see that there is a region in which the other fish don't go. No, they respect very much this privacy. So there is this space that it is only for the fish, and it's by the way of the order of 4 or 5 centimeters. So, and these fish are of the order of 2.5 centimeters. So it's a pretty large region. And it's very natural, right? Because if they occupy that region, the chances of not colliding or having a crash are much higher. So they are smart. And they will only diminish this region if there is danger around them, predators, and then they really squeeze and concentrate a little bit more. Otherwise, like in this swimming pool in which there is no danger, they will respect very much this space that it is just for each one. On the other hand, you will have a higher concentration of neighbors here laterally, with respect to the motion of these fish along these two particular directions. In general, on the lateral, also on top and behind, but more on the sides. And it makes sense, right? I mean, you don't want to be completely behind, because then if one breaks, you go and jump into it. So better not to stay on the side. I mean, we do that, right? I mean, unless there is no other option in the metro, maybe this morning you had to go like that. But if there is the option, then you will stay on the side, and it's much better because you have a much better view of what's going on, and you don't crash into the person that it is in front of you. They do the same, on average. Huh? Okay, so what I was telling you is that, I mean, we had, this model that we are developing, in which we have this idea that the motion of the fish with respect to the center of mass motion, which, by the way, is just a persistent random walk inside the tank, is something that you can emulate with this droplet, as if it was a liquid droplet, but with a membrane that it is weird. So most of the particles will be within the radius of gyration, but there are some that are actually able to escape and go out of the group, as you've seen in the previous animation, that, by the way, was an animation that was based upon the data, the experimental data. It's not something that I have invented, it's the data. So here, you can calculate what is the density as a function of the distance to the center of mass, or this centroid, and normalize it for the different system sizes that I am considering it in here in this way. And then, apart from the density being a little bit higher or lower in the inside of the radius of gyration, which is marked here with some red line that probably I don't know if you can see, the tails, which is farther away from the radius of gyration, they all collapse just by simply rescaling in this naive way that corresponds to the scaling that you will propose for a homogeneous system. So these fluctuations actually are similar in different system sizes. And if you were to imagine, I don't know how much experience do you have with equilibrium physics, for instance, in liquids. There is a theory that allows you to build what is the potential, the pair interaction potential in between two atoms in a liquid, according to the GDR. GDR is the distribution function around, one particle which is located at the center. What is the probability of finding other particles in a liquid at a given distance? Is the pair correlation function, is called the GDR. So if you know the GDR of a problem, and if you are in equilibrium, you will be able to, at first, in the first approximation, if it's not very dense and crowded, the idea is that you can rewrite the GDR as if it was some sort of a potential, effective potential, that it is confining the particles in the liquid together. So here you can kind of use the same type of ideas and arguments to try to figure it out what kind of potential you will have to actually plug in a model, in an effective model that drives the cohesion of the system to that area that it is this radius of gyration. So if you do that, I hope that you understand a little bit my words, and if you have doubts, please raise your hands. The idea is that inside it's like, freely moving. It's like a gas of particles that actually can be everywhere. So they don't occupy permanent and rigid positions, but they will be everywhere, without really interactions in there. But as soon as you get out of the radius of gyration, the idea is that you are going to feel an attractive force, which is something that everybody will use in order to model these systems. And this attractive force is different from what you had in mind at the level, for instance, of the liquids or other more in physical naive problems, traditional problems, let's say. So it's not going to be something that goes with R, like an oscillator or something like that. No. It's going to be something that it is constant. So the force that this particle that gets out too far from the group is going to be a constant force, according to this picture. It's It's just a picture. And this means that actually, if this is the group, and I'm going to explore what's going on around, I want to, be out for a while, it doesn't really matter whether I go out a little bit or if I go out a little bit more. Whereas, this is not happening in physics. And why is that? What do you think that can be, a possible solution for that problem, for this problem? It's because their vision is very long range. I'm going to show you experiments with a compartmented tank with two sides that they cannot traverse. And I'm going to show you at some point the high correlations in the motion of two subgroups of fish that are separated by a wall. When they can see each other, they move like if they were all in the same place. If they cannot see each other, then it's completely the opposite. So they really desynchronize in their motion. Okay? So this is nice. They have this long vision. And actually, the moment that I am able to keep control of where the group is, I really don't care whether I am here, very close to the group. This is the group. And where I'm here, because I see the group. So I'm feeling forced to go towards the group, but it does not really depend so much on how far I am, as long as I keep contact, visual contact with the group. This is something that maybe is happening in animals. Why not? And I can demonstrate that, long-range interactions are there through vision. I have these experiments that I can use in order to show you that. Okay? So this is one possible, for instance, interpretation that it is more coarse-grained, more physical, not so many parameters in this model. It will be a little bit more, simple and easy to understand. But this is work in progress, so I cannot tell you much more about that. We have a student that it is working on that, and maybe, hopefully, in a few months, the paper will be released and now for you to enjoy. What I'm going to explain to you is something that we have already published, and it has to do with your training. Yes, this is a school. It's not that I want to show you what we have done. It's true that I'm showing you what we have done, but it is probably a good idea that you know these things. Why? Because if you are working with other animals, maybe what we are doing in this context of fish is something that you can extrapolate and use in other contexts as well. So I'm going to tell you about this model, which is, well, it's not my favorite model, but everybody that is working with animals is playing a little bit with these kinds of models. So we did that, and we discovered something nice. So that's why we got it published. So I'm going to tell you about the typical effective force type of models, in which you will have repulsion, attraction, and alignment, all these things, more sophisticated than just the plain big shape model. But we are not going to use self-propelled particle models. It's not that. Why? Because we are going to keep inertia as an important still actor in the game. So it's just mass times acceleration equal to sum of forces. So it's not very creative. But what we are going to discover by using this type of model is something that it is interesting. Okay, so just I'm gonna go through the characteristics of this individual. This agent-based or whatever you want to call it, more mechanicistic model. So this is the picture. You are going to have alignment, repulsion, and attraction. These are what we call the social forces. But on top of that, you are supposed to be, as I was drawing in the blackboard yesterday, in a liquid that it is offering each element some friction when it's moving. And then you also have a little bit of noise acting on each individual. So it's not a complete picture with several forces playing a role. And with these kinds of models, we are not the first, of course, no. There are lots of papers on the subject. But with these kinds of models and touching a little bit the parameters here and there, you are able to reproduce what you see in experiments, all sorts of conformations and structures that are dynamic in time. So you can do reproductions of what you see in nature, that is this schooling fish, such as mine. But you could also pass from here to here, and having milling configurations. This is the experiment, and you can find these experiments in these journals here, 2021, 2022. So it's not very old. So it's something that is relatively recent. And swarming, which is what I told you that the zebrafish is doing. So the zebrafish, we have some in the lab. They just aggregate, like if they were feeling some sort of gravitational field or something like that, but they don't order themselves. So the velocity and the motion is not ordered, and they go around, and it's very random. So with the same type of model, you can actually reproduce whatever of these patterns, which is nice because you want to have a model that it is strong enough to do everything. And what I'm going to use now is to build these equations and talk about these effective forces, because they are effective, right? I mean, who knows if animals exert forces on the others? What we know is that there is a lot of decision-making at the individual level, and we are physicists, and we recast these decision processes that they do at the level of each individual in the form of effective forces that are like the forces that we use in physics in order to model the behavior of matter. And this is just active matter, but we consider it as matter. The inspiration of our work was in this paper here, where you have pairs of fish. One is the focal, and the other one is around. And that one around you is actually exerting an effective force where you are, and that effective force maybe have different components and different dependencies on the relative distance, but also on other variables, as you are going to see now in more detail in the next slide. Any questions so far? Yes. 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 The 3D. Oof. I don't know how experimentally. Well, you can do it if you have like different cameras, that are focused on different deepness, let's say, along the tank. We don't do that. So we have, a camera that it is on top, let's say, zenithal view. So you see, it is 5 centimeters. The tank, usually everybody will work in similar conditions. So it's not a tank that it is very, deep. So you have just a shallow tank, and you approximate the motion as like if it was bidimensional. But it is not true for birds, for instance. So they will have different cameras, and they will use these coordinated type of trackings, difficult to do, the most difficult part of that experiment, in order to reconstruct the 3D images. I am not able to do that yet. But for instance, the group of Irene Giardina and her husband in Rome, actually they are able to do that with the flocking birds, with the storninos. So that's the way to do it. And then you will have lots of trouble at the level of the numerics and the data. But if you read their papers, I mean, they provide clues about that. In the fish literature, what you will see is essentially 2D. Even if it's not strictly 2D, you will like the type of project what you see as if it was 2D without making too many errors. But it is true that the fish sometimes, that's why we have problems with the trackings. They go behind, and they pass on the third dimension in order to continue moving. Hopefully that's not very important. And in the whole duration of the experiment, because it's true that we have occlusions, but they don't happen all the time. They happen from time to time, and maybe they are not affecting very much what's going on for the rest of the experiment. Yes? You can do that in the models. Now we don't do that. So in these effective forces, here in this particular model that I'm going to explain to you, it's not the vision field, but we are going to talk about what we call selective interactions. So it's not that, but that is included somehow. Okay? It's more general what I'm going to describe. Yeah, there are many people, even us. At some point, I directed the TFM of somebody, and we were playing around with doing these big shape models with a cone of vision. And you can just play a little bit around and see that you have sometimes first-order phase transitions. This is done. I mean, many things have been done already, so it's difficult to find a little hole. But if you have experiments, then you're a little bit lucky, because then you have first-hand motivation to do things. Yes? Birds, you mean? No, I haven't done birds, but... Well, it depends on what you want. Yeah, from the point of view of the order and all of that, yes, similar, but qualitatively similar. Because of the 3D, for instance, the fact that, I mean, when they study birds, they are unbounded, so they are open in the air, there are no walls. Unless maybe Cousin these days is doing, Ian Cousin is a big guy, professor in the Max Planck Institute in Constance, and I know that he has a hangar, a huge place in order to do experiments. We cannot compete. But I don't know if he has done, like animal motion in there. I think that he's more focused on using the robots, the boats that go to the air, okay? The drones, So they are doing drones, and they also go into the swimming pools to do fish. So and in the swimming pools, they mix now fish that are real and fish that are virtual, and it's, incredible. Okay, there is a lot of room for you to work, huh? So this is encouraging. So it's not a closed field. There are many things that you still can do. So that's the nice thing. So anyway, so this is one of the papers, the pioneering papers already in 2011, in which they proposed this idea of having effective forces. And we are going to copy that. So we had this student, Andreu Puy, that went to Germany, actually, to the group of Paweł Romanchuk. He was doing all these models all the time, so he went there and learned a little bit, how do they actually were implementing the tricks and things like that. And we did that. So we proposed a model, which is already with several parameters as well. Acceleration mass is going to be considered equal to 1. Forget about it. Just we can include it into the time unit. Acceleration is equal to the sum of forces that each individual here is feeling, and all these forces are there. So the attraction repulsion that I'm going to explain in a moment, the alignment force, which is represented here, and then the friction propulsion, well, is the typical drag force that you will feel by the fact that you are moving inside a fluid that it is viscous, and then the noise, as I was telling you yesterday. The movie is strange. Anyway, doesn't matter. But for the attraction repulsion, here, I told you that there is no need to use a spring type of interaction, and I'm contradicting myself because here I'm using a spring-like. But it is not contradiction, because for this that we call social forces, the attraction, repulsion, and the alignment, we are going actually to use a wave that is inversely proportional to the distance. So this force actually is growing with the distance with respect to the preferred distance, that is this constant that we can extract from the experiments, this safety distance that they respect. But we are going to rescale it by this in such a way that if you go very far, the force is not going to be much higher. It's going to be the same, the same idea that I was telling you about. On the other hand, this wave, which is gravitatory in shape, let's say, is also going to pay more attention to the alignment with the closest nearest neighbors. This is some force that you will feel with respect to all your Voronoi neighbors in the model. This is what we call a standard model. Everybody could do that. All of you could do that. But it takes a little bit more time. Maybe you don't finish this homework today, It takes a little bit more of time. But the idea is very simple. So you write all these forces. This is the attraction and the repulsion. So the idea is that when this distance is bigger than the natural distance for this kind of oscillator, the idea is that you have attraction, the force is negative, so it pulls you back. Whereas, when this distance is smaller, then it rejects you and then actually pulls you out, changes sign, and actually becomes a repulsive force. Okay, but it is weighted, as I was telling you, with this factor that makes it not stronger when you are far away and not weaker when you are closer by, but it's going to be something that it is relatively independent on the distance of the neighbor. Okay. These are the ingredients. And then there is the propulsion. This is the typical form. So the idea is that if your velocity is not the desired velocity with which they move, you are going to feel this drag. And this is the drag coefficient that here is introduced in the form of this time, but it's OK. And then the noise that actually is going to be different along the direction of the velocity than in the perpendicular direction. This is just phenomenological, in order to try to see that the data and the model really go pretty well, not only in one observable, but in very many, okay? Understood? Yes, So this is the standard model. This is not our model either. I mean, this is something that has been already found in the literature in several papers. Yes. D naught is the preferred distance on which fish would like to sit. So I told you that they don't invade the distance that it is the private one. So they have higher tendency on average to be located at a distance of about 4 to 5 centimeters away. Exactly. So this is the distance below which you will feel the repulsion force, above which you will feel the attraction. And it's an average, because, of course, but for that reason we have here the noise, because the noise has to represent the variations in fish to fish, and the fact that you have maybe different distance. It's not exactly the same distance in front and behind and on the lateral side, but these details shouldn't matter. No, come on, you can just choose one distance on average, and that's it. Okay? Okay, very good. So if everybody understood more or less the ingredients, you will be able to put this model in the computer, use an Euler-Maruyama, simple code in order to integrate these differential equations. Be aware that it is not in the overdamped limit. In here, everything is included, the velocity and the acceleration, everything. And you will simulate that for several times. And now what I'm going to show to you here is what we call force or acceleration maps. So notice I didn't delete the dependencies of the different contributions of particularly the social force, that this attraction-repulsion depends on the relative distances. Whereas according to the introduction of this alignment, the alignment actually has to do with the behavior of the relative velocities. So alignment means that I want to be aligned with the same velocity, both in speed, so in the modulus, and not only in modulus, but also in direction with my neighbor. Okay? So it's everything that it is now here taken into account. So the fact that they depend on different variables is good to me. Why? Because I can concentrate in making this what we call effective force maps, so acceleration maps is the same, in which I'm going to average, for instance, over all the positions, or I'm going to average in the course of my simulations on the relative velocities, or on the velocities of the different fish that appear in the movie. And the idea is that since we have forces that are dependent either on the positions or on the velocities, we are hoping that by averaging over the distances or by averaging over the velocities, some of those contributions are going to cancel out, and I'm just going to get the dependence of these acceleration maps, different positions, as a function of the one that I haven't eliminated, as if it was some sort of elimination problem or some marginal construction of some sort of effective fields. Yes? So the idea is you have forces that depend on position, forces that depend on velocity. I have positions, velocities, accelerations everywhere in my 2D representation of the problem. And I can then perform averages the way, more or less, that I find that it is convenient. So what we are representing in here is the type of forces that you plug in into the model. This is what I am plugging in into the model. On average, I'm going to have a focal individual in the center, my nearest neighbor, and I'm just representing here what is the effect of this attraction-repulsion force that I put by hand in the model, what looks like when I average over all the particles sitting in the center and with respect to what you have around you at different distances. Yes? So this is more or less what you put in, so what you want, right? If you pay attention, you will have arrows going outwards within the central close region to the center. So this is because there is repulsion. There is a neutral region where actually there is not much of any of these repulsive or attractive forces. Doesn't mean that there is nothing, but there is less than here or there. And on the outside, you will have these attractive forces, so the arrows will be pointing towards the center in which you have located your nearest neighbor. See? So this is what you plug in, but average it over all the particles, taking into account the noises, everything that it is in here. Okay? So nothing spectacular. This is what I wanted. But now, what I want to see is what happens if I just get the acceleration field that this force, that this particle I is feeling, in the model after I have integrated and I have taken into account all the other forces. but averaging over the variables that actually I'm not interested in. So for instance, in this representation here, I'm just plotting the acceleration on average when I average over all times, over all the repetitions of the experiments, and also over all the velocities of the particles that are located at the relative distances that appear in this map. It's not trivial, but it's not very difficult either. So just you need some processing time. And if you do that, in the simulations that contain all these forces, they resemble very much what you plug in, which is something like that. Okay? So this is just, I'm not demonstrating mathematically anything, but I'm just showing to you that if you do that, it's not that bad, that you get in what you put in the model. And this is extracted from the behavior of the acceleration, which is like the force that every particle will be feeling in the course of this simulation, averaging, in this case, over the velocities independently of with what velocity my neighbor is moving at that particular position. Yes? On the contrary, no. On top of that, you can do the same thing, the same trick. This is just the representation of the alignment force that you plug into the model. So arrows pointing towards the center. Why? Because this is what you want to do. So in the center, you have the velocity of the particle, that it is the focal one. And I'm just flowing towards the velocity of that particle that I have in the center. So I want to resemble that variable that I have in the center. And you flow towards that. Okay, very good. And if you do the same trick of using the simulation, acceleration, and forces, it won't be so nice, but it's the same. So you see more or less the same type of map. So it means that in here that I am averaging over the relative positions. I just care about the velocity. The velocity is what it is represented in this axis. Forgetting about the relative distance of my neighbors, I'm going to get that, which is what I wanted. Is what I wanted to put in the model. Okay? So now, this is the model, just the model. I'm going to compare what I see in my simulation, in my experiments, with the fish, particularly for the alignment and for the attraction repulsion. Okay, first of all, here is just to tell you what I have said to you in words, that the rest of the forces that are there, including the individual forces such as the propulsion and the noise and whatever, when you average actually over the positions or over the velocities, since they don't explicitly depend on those quantities, you have you have same probability of having pluses and minuses and don't depend very much on those quantities. So we are lucky and we are averaging the effect of all those other forces to zero. And we are taking advantage of that to extract information from the acceleration maps. Okay? And that's now the comparison with the experiment, sorry. So this is the experimental acceleration of force maps that we will see in our experiments and that you have to compare with what you get in the standard model. Okay? So for the attraction repulsion, apart from the ellipsoidal shape that you see here, well, because the fish are elongated, we know that they are not round. So we see the similar thing, no? So repulsion at short distances, neutral in the middle, and attractive arrows, noisy but attractive arrows towards the center, which is not what we were expecting. So fish, according to this interpretation in terms of effective forces, are exerting mutual, attractive or repulsive forces depending on the relative position. This is a map, by the way, in terms of the relative position with respect to my nearest neighbor. On the other hand, if I look at the same plot that I was showing to you a moment ago, that I plugged into the simulations, and I compare it with what I see in the experiments, no similarity. No, you see some discrepancies. We are doing exactly the same trick, averaging here over the positions and just maintaining the dependence of this acceleration in terms of the relative velocities with pairs of individuals in between me and my nearest neighbor. So here I see some alignment, yes, but here, above zero, kind of, what we see is that the arrows, instead of pointing towards the center, which will reflect the pure alignment force that I have plugged into the model, what I see is what we call anti-alignment. This was something that we didn't expect. We thought that maybe we were doing some mistakes. So of course, we work a lot. We proposed several variations of the model in order to see whether we were able to get back this data, explicitly including anti-alignment. Many different things we tried, actually. We don't say it in the paper, but we tried several things. Until Andreu, this is the work of Andreu Puy, actually discovered that maybe we have this selective mechanism that I was telling you about. So we started now being very excited about the idea that, I mean, these forces, don't forget about it, are representing decision-making. I mean, there is nothing that physically allows my atoms to interact with the atoms of the other fish. It's not, those forces that we are describing in here are decision-making processes that are integrated into the form of these effective forces. So we thought about this idea that was working, of course, that fish that are fast are like exciting, like people that are sometimes more exciting than others. So those fish that actually had what we call strong movement cues means those that actually go faster, especially if it's not all the time, faster all the time, but they go faster. Or they turn more than others in their paths, in their trajectories, are attractive. So for those, I will put attention. I will activate all the social forces. I will try to align with those. I will try to actually attract and repel with those. And the ones that actually are slower than me, I don't care about. I don't pay attention. They are not dangerous. They are not maybe going to actually allow me to crash or something like that. That's the hypothesis. It's a hypothesis. These days, people will call that non-reciprocal interactions because, I mean, this is a social dynamics. And, I mean, the third law of Newton action-reaction doesn't have to be verified in these models. Why? I mean, we are reflecting here something that it is not physics. So we can violate that and actually take advantage of that. These days, several people in the statistical physics community will be taking advantage of this. There's non-reciprocity to observe new phenomena in out-of-equilibrium conditions. We didn't call it that because at that time maybe it was not so fashionable, but we call it selective. Selective in the sense that I select to whom I follow, okay? So this is what we actually tried and what we put into the model. So I don't repeat the equations, but the idea is that if my neighbor is going faster than me, in every general sense, in speed or because the velocity actually is very different from mine, if I'm in the upper part of this diagram in which I am representing the relative velocity, I will activate the social imitation forces. Otherwise, I switch them off in the same model. So switching on and switching off. Okay, maybe you like it, maybe you don't, but we have published the paper, so I don't care. So the idea is by doing that then, I mean, I agree it's not very clean, but I mean, we get something that it is more close to what we see experimentally. And we liked it very much, the idea. Moreover, okay, with that same model, you can also reproduce some other observables, not just the maps, which are, averages over many different things. And if you ask me, is just a unique way of modeling that? I cannot tell you that yes, because I don't know. Nobody knows. There are probably several models that you can use better than this, but we have tried several, and none of them were actually very successful in reproducing the maps. But not only the maps. I mean, we were also reproducing, as I was saying, before that, sorry. This is just an example, just a few snapshots. Here, if you are a little bit attentive, and this is repeating, it's just a piece that it is being repeated. So we are actually illustrating this selective mechanism. The idea is that there is a fish that it is the focal in green that aligns with the blue there that has this blue arrow because actually it's going faster. And he actually is not orienting himself with others that are around him that are also close neighbors but that are slower than him. Okay, more or less this is the idea. And this is what I am representing here. And as I was saying, we are not only reproducing the maps that we observe experimentally, but we also reproduce other observables that are interesting that we can control in our experiments, such as, for instance, the polarization distribution that we were also discussing a moment ago with respect to this big check variation with motion that it is oscillatory in time. So you can do that again with this model, and it's not that bad. And here, I'm representing the experiments in blue. The green is the standard model. The green is the selective model, the one that I have just discussed. And this will be the results by fitting parameters. Of course, there are parameters that you have to fit, but you extract some of those parameters directly from the data. They are here. And you do the same thing for the normal model, but if you do that for the normal model, You can reproduce, for instance, that the peak is in the same place. So the same parameters, once you have decided what are the parameters, you just plug in the selective interactions. You don't change the parameters anymore. But if you see what is the distribution of the polarization in the normal model without the selective social forces, you will see that this is the distribution. So very different from what we see in the experiments, whereas the selective interactions will allow you to find a much better agreement. Not only that, but also the nearest neighbor distances, distributions are very similar. The distributions of the areas of this convex hole, you know what it is? Instead of just talking about the radius of gyration that I was showing to you, it's just an effective way of representing the area of that group of particles that are co-moving with the center of mass. Now I just calculate the area of that triangulation that I have shown to you in some of the figures. This is the convex hole, it's called. It's the area that contains all the particles inside, okay? So you can control that as well. And also the duration of the contacts, how often they reshuffle the neighbors, These things, and many more that maybe you can imagine. With this model, you can get them kind of rather in agreement with the experiments, okay? Very good then. So go for it. So this is what we did. And not only that, maybe I have to go back to the transparency. Did you understand this idea of calculating also temporal correlations and to try to infer from those temporal correlations the leader-follower type of thing that I was explaining you the day before? So the idea, I just summarize it. We have the dynamics, right? So we can calculate correlations of the velocity, both its orientation or its modulus as a function of time for different time delays in between the different pairs of particles, if you want, in particular nearest neighbors particles, pairs. So the idea is that if my correlations are very high, when I am a leader with somebody that it is a follower, the correlations will be such that they are maximum with the follower evaluating its velocity at a time t plus tau being positive, right? Because he will copy me, I'm the leader, at time t, he will follow me and will be like me, giving me a big value of the correlations at a later time, because he's following me and it takes some time for him actually to follow me, although it's not very large. On the other hand, if me, the I individual, the one here, or I, yes, I am the follower, and I am at time t, and j, nearest neighbor is the leader. Actually, if it's the leader, I am following, I am at time t, I am following him at a negative tau. Why? Because actually he's the leader, I am at time t, and I'm following what he did in the past. So the maximum value of the correlation actually happens for a tau that it is negative. Why? Because he was the leader at time t minus tau. You see? This is stupid, but it is not, well, it's a way of inferring this type of temporal correlations that can allow you to introduce in the system some sort of leader-follower relationship. Yes, there is not such, there is not a unique way of doing it, but this is one way.
For this model, I would expect so that, because you're saying that you have a leader, and after a lag of time t, the others will follow this leader. But if every of the species would follow in the same t, I would expect that they would be also aligned.
Sure.
So I have a distribution.
So here I am actually representing the alignment because it's the correlations of the orientation. So one of these figures is the correlation of the orientation, and the other one is the correlation of the speed value. Both things are actually correlated also in the same way. So here, what I am representing is everybody with everybody. It doesn't really matter whether they are faster or slower. And then I am discriminating. And I am considering individual I, which is the focal, which is faster, to try to see if he plays the role of leader. And not the opposite way around. I'm going to consider I as the individual that it is going slowly at each time step, let's say. You can do that for every pair of fish. This is what we are doing in here, for every pair of fish that are nearest neighbors, sorry.
We should have a specific lag of time,
yes? Yes. So the idea is that if you are fast, our hypothesis is that you are calling the attentions of the others, and they will selectively adopt whatever your movement trend, let's say. Whereas if you're a follower, nobody cares about you. So now, what we are going to do here in this slide, maybe you don't see the point, is try to corroborate with a different way, apart from the maps that I have shown you before, that this is something that it is also corroborated by the correlations in time. So if you get those correlations in time, and you just select that the focal individual is a fast individual, what you will see is that the maximum value of the correlations with its nearest neighbor are going to happen at a time delay that it is positive. So I am actually a leader according to this definition, and he's going to be a follower that it is imitating me at a later time step. Okay? On the other hand, if I am a slow one, my correlations will be also high, but at negative times. Why? Because I'm following not the leader, which is the nearest neighbor, and then I will be actually doing what he was doing at some time ago. Okay? So this is what we do here. And we do it both for the orientation and for the modulus. So it works actually for both. And maybe another hypothesis, I know that Amalie had a question. I know that another hypothesis that you can find in many models around there is that the position matters. Of course, if you are moving in a channel, the position matters a lot. Right? If it's a one-dimensional channel, vision is there, of course, and then you are following if you are behind. But in here is 2D, right? And remember that I told you that fish not only have eyes, have also the possibility of sensing, especially nearest neighbors. They use that very much by the lateral line that actually has more to do with the pressure changes in the water. So actually, they don't need so much the eyes in order to see what is going on very close to them. Why? Because they can feel the pressure of the water around, and actually that indicates them that there are other fish around them, and actually they react to that in a way without really seeing them very much. I cannot do experiments in which they don't have eyes. No, they don't allow me to do that. But I mean, that will be the way to do it. I cannot do it. In Barcelona, I cannot do that. Okay, so yeah, the hypothesis there in general, in whatever dimension, is that the ones that go in front, there is in front and back, and that the leaders are the ones that go in front according to the motion. So we did that. Now we calculated these correlations in between nearest neighbors according to their position, is what you have here. Frontal and rear, you see? Frontal and rear, the curves that are, first of all, the correlations, at least the velocity correlations are lower than the ones that are related to the speed, to the faster with respect to the slower. But also they are not so significant. For instance, here you get higher, positive values of the toe when the individual actually is in the rear. So in this fish, I think that velocity makes more sense than position, because take into account that here we have walls. So they exchange very much the positions, and I think that it is more attractive, not really the position, because they don't go anywhere. They don't go anywhere. I mean, they are just moving around in the tank. There is no purpose in here, no escape from predators or anything like that. So in this context, at least, I believe that the velocity makes more sense as a mechanism to distinguish who is the leader and who is the follower. Movement cues, stronger velocities, higher turns, these are things that are calling the attention of fish. And one thing that I wanted to say, that also makes sense, right? A little bit from the maybe evolutionary, if you want, perspective. Why? Because even if we go in the metro, I do it many times, I'm going absent-minded, reading, maybe watching my phone or something, doesn't require so much of our attention to really, how do you say, grasp that something is going in front of you at the level of motion. So for me, to appreciate changes in the motion of other agents that are around me, actually don't have high cognitive demand. You go like that, absent-minded, and you can feel immediately just by maybe your eyes or whatever, but very fast, without really looking very precisely and making a big effort, that this is going to happen, that there is somebody that has to stop, that there is somebody falling there, and that you just need to brake, to stop. Don't you agree? I mean, I think that this is, from the evolutionary point of view, also something that makes sense. Because appreciating motion qualitatively is not so highly demanding from the cognitive point of view. I don't know, the people in the audience that know much more about the brain can argue about that, but it's my impression. Amelia. persistence in that trend of the velocities, no?
Because I figure if you have some fish that is slower in its reaction time, it will be more persistent than
You mean, imagine that I have determined that, whether, I mean, that is consistent and repeats itself, no, this pattern of no, we haven't done it, but I think that we can do it easily. But on the other hand, yeah, indirectly it's there, right? Because here we are actually getting every pair of nearest neighbors along the course of time and averaging overall, no, the time steps that we have over there separated by this window too. So, you know, but it is true that we are not demonstrating anything else than what we show in here, right? I mean, the fact that we have temporal correlations in this pattern is not there, it's true. Thank you. Yeah, we can take a look at that, yes. Because as I said, these fish, the moment in which they feel that they are not behind, will trigger these mechanisms to selectively copy the others. And I don't know how long does it last, but probably not that much. Then probably the thing changes and they become the leaders. I mean, I'm not saying here that there are permanent leaders. Don't take that idea with you home because it's not the case. The idea is that they transiently can play the role of a leader and some others, the follower, and the opposite way around. And the imitation mechanism of this velocity is not what I'm doing here and what I want to convey to you is that if you switch on and off these mechanisms according to this selective rule of interaction, of social interaction, with that you can reproduce nicely some of the experimental evidence that we have. It's true that maybe some of the people will get some of the fish and maybe there's a contradiction. We will see that, because it's published, so the literature continues, and we will see what is the end of the story.
I was thinking that, like, biologically, these fish are, well, they are prey, right? And usually prey are very sensitive to sudden changes in environment.
Yes.
So do you think this kind of like transient leadership behavior is emergent only from the fact that these fish are sensitive to, or like the behavior is sensitive to weighting regarding the other fish's speed and velocity?
Maybe.
Yeah.
Yeah, makes sense. Yeah, it makes sense. We wanted also to do experiments in which you trigger startles, like you scare the fish and try to see what happens. Have you used some of those yourself? No. Oh. No, they don't allow me to do that. No killing. Yes. So we have now, well, I had all the ideas. I'm very creative, but then I don't have, then I don't have the hands to do everything because of the trackings I told you. So we try, yes. So I had, like little balls and, like some kind of cylinders there that I put in the middle of the tank. And the problem there is that the tracking was not working, so it's horrible, unless we have very few fish. And this is something that somebody else has already done. I thought about it first, but it's already published. So there is a group in Grenoble that has done that also with fish. So you can, I don't have the paper here, but it's Philip Payla. I don't know them personally. At some point I will, but yeah, they had similar ideas to what I had in mind, and they did it first, but with very few fish. So what I have done now is experiments in which we have this dividing wall with a door. And it's very nice because you can understand how they cross from one side to the other side of the compartment and understand, whether there are correlations in time, how often that happens. And this connects with my last part of the presentations that maybe is going to be tomorrow. That has to do with these cascades that we see in the motion of these fish. Like if they were critical systems, close to a critical point. So we go back to the idea of this criticality in the brain, in the superorganism, this picture that I proposed you in the very beginning. Okay?
Have you ever tried, since those forces might be selective forces, have you tried experimenting with predator on the same scenario or on stimuli with?
Stimuli we can do predators, they don't allow us to do. It's not a joke. We have this facility in Barcelona in which they have rats and all these animals for experimentation, and including us there, we have this little room, right? So it's very hard, no? So we have all animalist people that are paying so much attention to what you're doing there. And the University of Barcelona has appeared, no, Albert, several times in the news for some mistreatment, of some killings of animals. So I cannot put a predator in there. They don't allow me to do. Every time that I do something, I have to write a report telling them exactly what I'm going to do. Whether I have to do it or I could do something to treat them nicely, it's pain in the ass. So no predators, but stimuli, yes. Like maybe dropping a drop of water. Yeah, things like that, yes.
But what about for the friendly? You've done some experiments on invasive species and their native behavior species and response to invasive species.
Exactly.
And we
Yes.
use both aquariums that the species they didn't interact, but they had like visual.
No, that's a good idea. I didn't think about that, you know? Very good. So maybe we can put in one side of the tank the zebra and in the other part of the tank the black neon and see what happens. I thought about mixing them. This is something that you can do, but the poor guy working there in the place will have them to remove one by one, each fish, and return them and separate them. Behind all this research, which is nice from the point of view of the modeling, there is somebody there that it is cleaning the popo of the fish, taking care of the pH of the water, making these recordings in a room that it is relatively hot, Yeah, I'm not just complaining because it's what I wanted to do, but yeah, you cannot do everything and very fast, so you have to be very patient. Now I appreciate very much the work of experimentalists. It's a lot of patience that you need. But yeah, very good idea. Maybe we can discuss later on and try to see whether, makes sense. I don't know if probably they don't care about what they see, or maybe they do. I really don't know. It's like an attractor. I don't know. Very good. Any other question? Yeah. So what we have done here, if I understood correctly, sorry, what we have done here is not just comparing one system size. These experiments that we've done also with this model with selective rules of interaction, are repeated and compared with different sizes of experiments with different sizes of the group. And similar, even with two works more or less. With two fish, these ideas work as well. But the drop, I don't know what is the drop. The drop, you mean the size of the effective area where they usually are? Yes? The group, you mean? Well, what we do in this model actually is really cleaning that up a little bit, because what we say that matters the most is the closest neighbors. Remember that this alignment force is weighted with some inverse over the distance with respect to my neighbors. So I'm paying more attention naturally in the model, this is my hypothesis, to the ones that are closer to me. I don't care so much if I have big group of 40 if they are far away and are not my neighbors. So it's local decision making, local, at the level of local fish, okay? Maybe you come out with another idea. I'm not saying that this is the whole truth. This is not the Bible, no. But this is one hypothesis that's nice and that we got published, and we were happy, although maybe the model is not my favorite one, because there are several adjustable parameters, as you see, and I hate to have too many. But this is what we could do, and we are working heavily also in proposing other more coarse-grained models that are maybe more physics-like, more physics-like. So this will come later, and tomorrow we start with that. With the intermittent, I think that this is the right time to stop, and also the time. Okay. Very good. Thank you very much for your attention, and I'm here for your questions, whatever they are.